Yeah, you can go all the way back to the beginning of the semester. Nothing in Canvas should be closed. You should be able to go back and redo anything and everything.
That's due tonight. Is it the last homework for?
Yes, it is the last homework for the whole semester. Yep. I know, right? Okay. So I want to talk about another important concept. Thank you, ma'am. Tomorrow you guys are going to be exploring around with this concept. So I want to talk about it today so that you have some skills to work with tomorrow as you investigate some of these relationships on your own. Okay? So the relationship between perimeter and scale. Start off with just remind me, what is perimeter?
All the sides?
Add up all the sides. It's the distance around the outside of an object, right? Perimeter is distance around the outside. And on Monday, we were finding area and perimeter of different irregularly shaped objects, right? When we found the perimeter of these objects, some of these objects were measured in inches, some of these objects were measured in millimeters or in meters. When we found the perimeter, did we use just the units as they were given to us on the picture, or did we do things like inches squared or centimeters squared? Did we do something like that for perimeter? You can go back and look if you want to. When we did the irregular objects, we were talking about perimeter. No, we didn't have any squared units there. Because how do you find the perimeter? We know it's the distance around the outside. What operation did we keep doing? Addition. When we are adding and subtracting things, the units don't change. It's going to stay inches or it's going to stay centimeters. The scale, do you guys remember when we did the math activity and I had you measure the little the legend and we figured out how many miles were in 1 inch? And then we know in real life that Indianapolis and Chicago aren't 4 inches apart, right? In real life, they're much, much farther apart. But we can have these scale maps. All of our maps are representing real distances just using smaller sizes, and then they tell us what that scale is in the legend. Or one of the other activities that we did using scale was when we looked at the Eiffel Tower and the Washington Monument. You guys remember looking at those two pictures? We were trying to figure out which one was bigger, and they'd put a grid in the background. Do you remember doing that at all? It's in your book. Where else did we use scale? When we looked at the house plans, like the apartment plans, when you go and you guys start looking for a place on your own, a lot of times you're like, okay, it says it's this many square feet. I don't really know what that means. I don't really have any concept of how big that is. Like, how big is the kitchen? How's it laid out? Is it going to have a window in a stupid spot? Where am I going to put my couch? You want to see a picture of it before you drive all the way out there and take the time to go look at it, right? Or especially after you've looked at it, if you're trying to show your friends and family, like, this is the place I'm going to rent. This is what it looks like on the inside. Those floor plans you can show to people, and you're like, here's where my bed's going to go. Here's my dresser. Here's my nightstand. Here's where the TV's going to be. You want those to be accurate, just smaller representations. That's the piece of information that we are given with the scale. Scale is what we multiply or divide by to keep things in the correct proportions. So scale, what we multiply or divide by to keep correct proportions. It's what allows us to make maps. It's what allows architects to make blueprints, so that then other people are like, okay, I know how big this should actually be. The relationship between the perimeter and the scale, we're just going to multiply or divide by whatever our scale is. I've been using a lot of examples here of times that we have something that's actually big in real life, and we need to shrink it down to fit on a piece of paper, like a map or floor plans. There are other times that we go the other way around. Have you guys ever had to draw a model of a cell, like in a science class? Are cells really as big as you draw them? No. We make it much bigger so that we can identify all these different pieces and we can actually see it. In that case, if you draw a model of a cell and you draw it accurately, or the ones that they have in the books would be accurate, right? To find out the real size, you would divide by something because it's really much smaller in real life, right? So that's why we say multiply or divide. It depends on whether the real object is actually much bigger than our representation or actually much smaller than our representation. The relationship between area and scale. When I'm talking about area, what does that mean? It's what? The space inside an object. What type of object? Any object? Is area the space inside this object?
No.
What do you call the space inside an object like this? Volume.
Oh, for real? I thought that was only the cylinder.
No. We are going to talk about cylinders today, though. So when you say the space inside an object, I totally agree with you. That is correct, but let's be really clear about what type of object. It's not a three-dimensional object like this, right? It's a two-dimensional object, so some kind of flat object. The area is the space inside a flat or a 2D object. Scale is still whatever we multiply or divide by to keep our correct proportions. Oh, I grabbed an extra piece here. When we were finding area on Monday, what operation did we keep using? Multiplication. We would take length and multiply it by the width, right? Area is equal to length times width. What kind of units were we ending up with? Square units. Because we were doing things like inches times inches, feet times feet, meters times meters. Just like when we do 5 times 5, or x times x, we end up with these squared units. This would be 5 squared. This would be x squared. So when I have inches times inches, I get inches squared, right? So the relationship between area and scale. I want to draw a little picture off to the side, and we're going to see if we can find what this relationship would have to be. So I want to pretend for just a minute that I have this rectangle here, and it's 5 inches by 2 inches. What would the area of that rectangle be?
10 inches squared.
10 inches squared. What if I wanted to take that rectangle right there and I wanted to double the length and the width? What would the new length be? I just want to double the length and the width. I'm not talking about area yet. What would this change to if I wanted to double it? 10 inches. What about this side? 4 inches. Oops. So if I drew a new rectangle that was 10 inches by 4 inches, what would my new area be? 40 inches squared. If I double my dimensions, that means my scale is what? What did we multiply by? 2. But what happened to my area? Did my area just get multiplied by 2? It got multiplied by what? By 4. Huh. Why? That original area was 10 inches squared, and it gets multiplied by 4 to get the new area. Well, we have length and width, right? We have 2 different dimensions that changed. The length doubled, and the width doubled. So I multiply by 2 here, and then I multiply by 2 again here. So I have 10 inches squared, but then I multiplied by 2 times. 1 for the length, 1 for the width. Does that make sense? And that's how we got this 40 inches squared. So the relationship between area and scale, whatever my scale is, it's going to be my scale squared. Multiply by the scale squared. Why is it squared again? Other than because Ms. Bolt said so?
Inches? 2 inches?
Not just 2 inches, but what changed in size?
Area.
My area changed in size, but before my area changed, what else changed? The length and the width. We doubled the length, we doubled the width. So I multiplied by 2 for this dimension, I multiplied by 2 for this dimension. So I did it 2 times. So this 2 right here is the number of dimensions that changed. In this case, it was length and width, right? This relationship between scale and area can also be used when I'm finding the surface area. Do you guys know what surface area is? What is surface area?
The surface in there. It's the area of the surface of the object.
That's exactly right. It is the area of the surface of an object. This right here is a great example of surface area. I pulled this out before because you said area was the space inside, and that is true, but specifically area is the space inside a flat object, 2 dimensions. Volume is the space inside a 3-dimensional object, length, width, and height. When I'm talking about surface area, that would be how much I need to cover the outside of this object. So if I wanted to paint this object, the surface area is how much paint I would need to cover it, not how much paint I would need to fill it, how much paint I would need to cover it. Or if I wanted to wrap it, because everybody once writes rice bits for Christmas, right? How much wrapping paper I would need to cover the outside of this object. Or this particular object is made out of cardboard. I could take it apart and lay it flat, right? It's how much cardboard it took to make this box. That is the surface area. So far, so good? Cool. Let's start using this in some applications now. Look down towards the bottom of the page. I know that the surface area of a cone is 38.2 square inches. How many dimensions are we talking about when we say area? Area has how many dimensions? 2. It has length and it has width. Area has 2 dimensions. If I quadrupled, what does quadruple mean? Multiply by 4. If I quadrupled all the dimensions, I want to know what the surface area of this new object would be. I'm not telling you the original length or the original width, but we do know this relationship. The length is going to be quadrupled. The width is going to be quadrupled. So how many times am I going to multiply by my scale?
4.
What is my scale?
Hold on, wait a minute. Is it 2?
Scale is what we multiply or divide by. What does quadruple mean?
4.
Specifically, quadruple means to multiply by 4. So what is my scale?
Multiply or times 4?
Times 4. My scale is 4.
Multiply 4.
This is how much the length and the width are going to be changing by. They're going to be changing by a multiple of 4. Since I'm talking about area, that's how many dimensions? 2. How much is the length going to get multiplied by? 4. How much is the width going to get multiplied by? 4. So how many times are we multiplying by 4? 2 times. Once for the length, once for the width. Without even seeing this original object, I can figure out how much cardboard or how much wrapping paper I would need for this new, bigger object. Go back and look at what we said. What's the relationship between area and scale? It's got a big purple squiggly box around it. What's the relationship between area and scale? Multiply by the scale squared, because the scale is going to change the length and it's going to change the width. What's the area of my original object? 38.2 square inches. I am going to multiply that by my scale. What's my scale?
4.
4 because it said quadruple, but we're changing how many dimensions here? 2. So in here is the scale.
Wait a minute, I got a question.
Uh-huh.
Area is always 2 dimension, right?
Yes.
Okay, so always multiply that number, whatever it says quadruple, should be by 2.
Not multiply it by 2, but make the exponent how many dimensions you have. Yes. So if it says area, your power is going to be 2.
Okay. But if it says perimeter,
If it says perimeter,
add by 2.
we would just multiply by our scale one time because it only has one dimension. I can take a single piece of string and drag it all the way around the outside of this room if it was big enough, right? Or I could go and buy a skein of yarn and drag it around this whole room, and then I could lay it out flat in a single line. That's one dimension. If I want to talk about the space inside, length and width, I'm multiplying pieces together. To fill the floor with yarn would be very different than just going around the edge. Does that make sense? Okay. So I want you guys to grab your calculators then and tell me, what would the surface area of this new, bigger cone be? $611.2. Almost done. What's my units? Inches squared. Why is it inches squared again? Yep. The scale didn't have any units with it, so I don't need to change any units here. It's just getting bigger, multiplying it by 4, but we're staying in the same units. So far, so good? Okay. Look down at the next one. Rectangular prism, which is a fancy way of saying a box. So I got a picture of a box right there. What are the dimensions of the box that I have showing? 7, 3, and 4. What do I want to do to all of those dimensions? I want to double them. So what's my scale then? Scale is 2. What would the new height be? 14 millimeters. So I'm going to write that on this bigger rectangular prism over here. What about across the bottom where it says 3 millimeters on my original object? 6 millimeters on my new bigger object. And what about where the 4 is on the original? 8 millimeters. Everybody comfortable with that so far? Did we double all of our dimensions? Cool. We want to try to determine the relationship between the larger and the smaller, what's that last word? Volume. How do you find the volume of something? Length times width times height. So how many dimensions are we talking about now? 3 dimensions. Let's find the volume of this smaller one first. If I want to find the volume here, length times width times height, what am I multiplying together? 7 millimeters times 3 millimeters times 4 millimeters. So let's pop that into our calculators and see what we get. How much? 84. That would be 84 what? What would our units be there? Millimeters cubed. Why cubed? Because we're multiplying it by itself 3 times, right? So just like 5 times 5 times 5 would be 5 cubed. X times x times x would be x cubed. Millimeters times millimeters times millimeters gives me millimeters cubed. Beautiful. Let's come over here to the bigger one. Let's find the volume here. What are we multiplying together over here? How much?
672.
Yep. 14 times 6 times 8 millimeters on all of those. And Fabiha, you said that's how much?
672
672
millimeters.
millimeters cubed. Love it. Let's see if we can find a relationship here between the smaller one and the bigger one. Because it'd be really helpful if every time I enlarged it by the same amount in each dimension, I didn't have to draw a new picture and recalculate it all over again. So we took our original volume, right? What did we do to each of those dimensions? We multiplied by 2. So here's my scale. How many times did we multiply by 2? 3 times. Why 3 times?
Because we multiplied by 2 to 3 different numbers.
Yeah, we did it to the length, we did it to the width, and then we did it to the height as well. This was the number of dimensions. Length, width, and height. So the relationship between my volumes is going to be my scale raised to what power? To the 3rd power. Every time when I'm talking about volume, because volume always has how many dimensions? 3 dimensions. Area always has 2. Volume always has volume 3. Perimeter has 1. There we go. So volume my scale cubed.
Volume scale is 2 at the top.
Up at the top, the scale for this one came from right here. We doubled all of our dimensions. So the scale on this particular object was 2. Does that make sense? Okay. I want to look at the next page a little bit. Nope, unfortunately, we're not done. I have a new object here. I wasn't lying when I said we're almost done. What kind of an object do I have here? A cylinder. Which one have they given me information about? The smaller one. What do we know about this cylinder? We want to find the volume. Do we know anything about the height? Where would that be on my picture? Where would the height be?
5 centimeters.
About 5 centimeters, yeah. Here's my height. There's an issue, though, when I'm talking about length and width. What shape is the base of this cylinder? It's a circle. Do circles have length and width? No. Not really. They kind of do, but not really. If I were just multiplying length and width together, what would I be finding? Area. So I'm taking area of one surface and multiplying it by the height. How do I find the area of a circle?
Isn't it like the radius and the area?
No, you got this right. volume of a cylinder would be equal to, we need the radius. I need 2 dimensions for area, right? Length and width. But we use the radius for both of these. So we're going to square it because I'm multiplying it by itself. Radius squared. And then I need one more important piece. Pi. Pi r squared times the height is how I find the volume of a cylinder. Okay, so you told me the height was 5. Do I know any other numbers about this cylinder? The diameter is 4. What does diameter mean? Yeah, from edge to edge, right? Do I use the diameter when I'm finding the area of a circle? I need the radius. How can I use that diameter to help me find the radius? Half of it. So how big is my radius? 2 centimeters is my radius. Do we have enough information now to find the volume of this small cylinder? Let's go ahead and do that. So volume is going to be equal to pi times what? Times 2 what? 2 centimeters. What are we going to do to that radius? Square it. And then we also multiply by what? By 5. 5 what? Centimeters. Grab your calculators. As far as the numbers go, we need to multiply pi times 2 times 2 times 5. We're going to round this to about 2 decimal places. 62.83. What kind of units would we have on that? Close. Y cubed. It is volume. We're working in 3 dimensions. Look at what we did to the radius. We squared it. That radius had units on it, so I did centimeters times centimeters. And then the 5, the height, also had centimeters on it. So centimeters times centimeters times centimeters again. All right, so there's my volume of the smaller cylinder. What does it tell us we want to do to all of the dimensions? Triple them. So what's my scale? 3. Can we figure out the volume of the bigger cylinder without having to draw in all the new dimensions and do the volume formula all over again? Tell me how to do that. I can find the volume of this cylinder by doing what? Yes, we're going to take the volume of the smaller cylinder, so 62.83 centimeters cubed. We're going to multiply that by, I'm sorry, one more time for me. Scale to the 3rd power. So I have 2 3's here. What is the 3 inside the parentheses telling me? That's my scale. What's the 3 outside the parentheses telling me? That it's volume because I have how many dimensions? 3 dimensions, length, width, and height. This is the number of dimensions that are changing. All right, so I want you guys to do that for me now. Multiply that volume that we originally came up with by 3 cubed to find the new volume. We're going to round it to 2 decimal places as well. Yes. 1,096.41 centimeters cubed. Beautiful. So we're going to generalize this idea now. I know those lines down below say, like, what is the relationship between scale and volume? We're going to write that down, but then we're going to take this out even further. So on these lines right here, scale and volume, can you tell me what the relationship is? Yes. Scale to the third power. If I wanted to do this for any number of dimensions, I would take the scale to the power of however many dimensions I have that are changing by that scale. If we had 4 dimensions, if we had 5 dimensions, if we had 7 dimensions, however many dimensions I'm talking about, that's what my exponent's going to be. Because that's how many times we would be multiplying by our scale. Does that make sense?
Yep.
All right. I want to apply this to 2 more problems and call it a day. And tomorrow I'm going to give you some time to experiment around with these ideas, and you're going to extend it a little bit further through some exploration. So I've got 2 problems down here. I know the surface area of a cone is how big? 430.8 square inches. When I'm talking about surface area, how many dimensions are we talking about? 2. Area is always 2 dimensions. What do I want to do to all of those dimensions? Double them. What is that telling me there? The scale is 2. What would the surface area be of the resulting larger cone? Tell me what to do to set this up.
430.8 inches squared times 2 squared.
Yes. Times 2 squared. We have our scale here. We have our number of dimensions here. So let's pop that into our calculator then and find out what we get. How much is the new, bigger cone?
1,723.2 inches squared.
Yes. Last problem. Read it carefully. A square pyramid was enlarged by quadrupling all the dimensions. What are they telling me right there?
Scale is 4.
Scale is 4. The resulting volume, what are they telling me right there?
This is
After
after we've quadrupled all the dimensions.
we've quadrupled all the dimensions, how many dimensions are we quadrupling here? When we say all, and then I say volume, 3, because volume has length, it has width, and it has height. So volume tells me right here 3 dimensions. And you keyed in on the resulting. So the resulting volume of the larger pyramid is this big. What do I want to know?
Your original pyramid size.
So should my answer be bigger or smaller than that number they gave me? Smaller. Do I multiply to make things smaller? I divide. So I'm going to have a fraction here. For my scale, instead of 4, it's going to be 1/4 to make it smaller. Fractions make things smaller. Whole numbers make things bigger. So I have 7680 centimeters cubed. What am I going to multiply this by? 1/4 squared? Cubed. Why cubed? Because it's 3 dimensions. So it's getting smaller by a scale of 4.
No, students, we have one cancellation. The White Gospel will not be meeting this afternoon. Again, the White Gospel will not be meeting. Go home. Thank you.
How big was the original? 120. All right, ladies and gentlemen, before you leave the room, in the black tray over here is the practice test. Please make sure you grab a copy of the practice test on your way out the door. Have a wonderful rest of your day, and I'll see you guys tomorrow.